The exhaustive mathematical computational steps are simply minimized. How is that? A simple narration says dynamic programming method is applicable to a process or an decision taking activity where series of decisions need to be taken, and the decisions taken at certain step and the next subsequent step and the next subsequent step are interconnected by this concept that is called as optimality principle. So in which our power system likely where the load at particular hour number mid 12, 1 hour later, another 1 hour later, like that hourly if I stagger it, definitely it keeps changing. So decisions taken at hour number 12, decision taken at hour number 1, 2, 3 keep on changing. Now where this dynamic programming is applicable, whatever is the initial conditions at certain decision step, whatever the decision you have taken, whatever is the output you obtained, see to it that remaining decisions which are pending to be taken should constitute optimality on the outcome obtained from the previous decision, like that. If there are 3 decisions to be taken in a process, take a decision at stage number 1. Do not worry about what is the decision you have taken. Worry about output of that with the remaining 2 decisions to be taken, such that they will try to optimize the output to the requirement. In that way, whatever is the initial condition, whatever is the initial stage, the outcome which has come, on that we have to act. The remaining decisions must constitute optimality on the outcome obtained from the previous decision. So then second stage decision you have to take such that you must try to get best outcome from the input available as an output of stage number 1. Do not worrying about what was the decision and simply worry about what is that decision. It must be taken at stage number 2 so that input obtained is able to get into best product from the out of the second stage. Then it has gone to output of the second stage out and entered as a stage number 3. You are left with only one decision as an example of 3-state example decision. Whatever is the previous state, whatever is the previous decision, now you must see to it that current decision which is pending, which must constitute optimality on the outcome obtained from the previous output, which is nothing but second stage output, which is an input for the third stage. There I must initiate a best control so that output after the third decision, which is a final decision example, should be an acceptable to your requirement. In this regard, at the third stage, it is not questioned what is wrong at stage number 1. What is wrong at stage number 2? It is questioned what is that best it can be done at stage number 3 to see to it that input what is being obtained at the inlet of the third stage can be processed as a best output at the end of the third stage. In this way, series of decisions need to be taken. Then number of decisions taken are straight away reduced to number of components. Like in case of a power system, if there are n generators, like n equal to 4 on my slide, 2 raised to n minus 1 combination, I need to check if it is a simple priority listing method and other techniques. If I follow strict dynamic programming method or a dynamic programming method, I need not check 15 combination for a 4 generator decision process, 2 raised to 4 minus 1. These 15 I need not worry. I worry about only n, 2 raised to n is 4. Only take 4 decisions, 4 priority decisions, that's the end. If I would have taken a process of simple enumeration or a priority listing method, 15 combinations I must evaluate, compare, take decision continuously at each hour of your decision process. So that cumbersome work is eliminated by dynamic programming method. It makes it straightforward. If you have those many units, only those many decisions are left. How is that being done then? It again follows. Dynamic programming method always again follows a simple technique. If there are n units in the combination, you have to make them ordered on the priority basis. Either you order them on the priority, either on the merit of 1, merit 2, inferior to the merit number 2, 3, 4, like that. Some certain combination you have to make. That need not be even a merit also, to be frank. It is just a set. In the set, you should have number of generators. So, better is you can keep them in the proper order. Then, among the total generators in a string, you have been put with a certain task. Suppose there are 4 units only. You are left with 4 decisions. Then, for a particular megawatt to be generated and delivered to the plant, among the n generator or among the 4 generator, which is the generator you are likely to take up first and start producing megawatt from that and deliver the load. That's called your first choice or a first decision. So here you need not worry about machine number 1 you would like to pick, machine number 3 you would like to pick, machine number 4 you would like to pick, or n. That is the definition. Whatever is the initial stage, whatever is the initial decision, worry about the output of decision, and a subsequent decision to be taken should constitute policy, optimal policy like that. So in my example of 4, there are 4 generators. I will pick one of the 4 machines as my first choice. Then I will generate megawatt from minimum to maximum possible from that generator. So my experience says, by the operation point of view, certain generator of the 4 I have picked. That is called priority 1. First priority. 1 shall not mean machine number 1. 2 shall not mean machine number 2. It is the priority of your pick. You have picked from the 4 one of the generator, which is your first decision completed. So you are not worrying about the decision. Why you took generator number 3? Why you took generator number 2? It is not a question for you. The question is you have taken a decision. That's all. Now you are left with second unit to be combined. Now you are left with 3 generators. Out of the 4, one of your best you took. Remaining 3 are there. Certain megawatt and above, unit number 1, your decision 1 cannot fulfill. Then you are accustomed with the second decision. Take one more generator from the remaining 3 generators to be combined with the previous decision, so that these 2 generators together can certainly develop a megawatt, meet the requirement of the load. Then you took from the remaining 3 generators of your best choice. So how you have taken a decision? It is a question. You have taken a second decision. What is that priority? Whatever is the first decision, whatever the remaining decisions which are left should constitute optimality on the outcome obtained from the previous decision. Now the choice is, which is the machine you are going to pick, play a role here, because first decision already gone. Its output is already obtained. It is not fulfilling your current load requirement. Then your mandate to take a second generator from the remaining 3 machines. Then why you took certain low capacity generator, why you took certain large capacity generator, that is not the question. The question is, you have picked a machine and it is generating for your requirement, and at a point it is unable to produce the megawatt required. You are custom with a second generator to be combined. Then when you want to combine, you should see to it that from the remaining set of generator, you combine the one with the previous, so that those 2 can meet your requirement continuously further. So now the question is, you took a decision 1 for a certain megawatt, that is the best decision, it is initial decision for you. Suppose the load is from minimum to the maximum capacity of the generator you have took, that will fulfill your requirement, and the load is increasing beyond that, say 100 megawatt. Definitely machine number 1 is suppose capable of 100 megawatt, it cannot fulfill more than 100 megawatt. Then you took a decision number 2, which will combine 100 plus say another 100 megawatt. 200 megawatt, these 2 decisions can support you. Now, the dynamic programming method says the second decision should be so optimal It is working on the outcome of the first decision such that decision taken at 2 will constitute best pair with the previous output. It will fulfill your requirement till their capacities. The question comes here. Among the 3 remaining generators, what is that I have to pick as a second decision? That is the intelligence over here. Among the 3 generators, best generator capable of cost effectively, that should be combined. Even you need not do it. That again says, whatever is decision initial, whatever is the outcome obtained, take a decision which constitute optimality on the outcome of the previous. That means what? The decision what you are likely left to be taken should constitute good result on the output of the previous decision, so that the choice of machine 2 should be superior from the remaining 3 generators. So this way, these 2 stand as best pair in future also. Whenever load certainly falls, say 100 megawatt, 100 megawatt, load is of 200 megawatt. This is the only combination fulfill the requirement best way. That way, this stand as a reference in the system. Suppose load is increasing beyond 200 megawatt. Say 100 megawatt plus 100 megawatt, load is increasing. Hour number 3 or hour number 4. You are left with one more decision. Load is increasing, another machine you have to combine. You are left with, out of the 4 generators, 2 decisions you have taken. 2 generators are remaining in the set. Which is that you take now? Among the 2 generators, which is the cost effective best one, you will combine. So that becomes a 3rd decision. While taking the 3rd decision, you are left with the 2 generators in the basket, means in the decision basket. Whether you take the one or the later one doesn't matter. What matters is what is that you pick. That should constitute optimality on the decision taken previously. What was your previous decision? Previous decision is unit number first choice, unit number second choice, together were fulfilling 200 megawatt. Now that is your previous decision. On the outcome of decision, 3rd decision should work such that output of 3rd decision should be optimal and best to go for next stage. Then you combined one more generator to the previous decision, so that decision number 1, decision number 2, decision number 3 has come. So these 3, suppose 100 megawatt, 100 megawatt, 100 megawatt, if I consider, they will carry the load up to 300 logically. So later 300, suppose demand is increasing on the station. I have no option. I have left with only one decision in the basket of decisions. So that I will combine. So you can see priority number 1, which I took when 100 megawatt was the load. Priority number 2, when the load was up to 200. When the load was up to 300, load more than 4, up to 400 and equal to. So this way, how many decisions I took here? I took only 4 decisions, keeping that when I want to operate the power system, if the load falls about 100, the decision what I have taken is best. Decision 2 is when the load is 102, suppose say 200, one of the machine which is picked here, so its identity, it is unit number 7, unit number 3, like that, number must be given. That is the combination with the first choice, together can fulfill your next slab of load, next slab of load, next slab of load. Like this, how many decisions I took? In overall, I took only 4 decisions. Number of decisions permitted for you, that is the only decision. So here I took a case, if there are 4 generators, how you combine all the 4 to meet your requirement using dynamic programming method. This is just an outline. Take decision number 1, work till its max capacity. Certainly you are left with load shortage, generation shortage, deficit. You are combining with another one, which is another second decision. Second decision should be optimal on the outcome of the first, so that it is better in the next comparison. Likewise, only n decisions are left here. So while doing this, it takes some assumptions. It is a mathematical computation method. It says no load costs are 0. Unit input output characteristics are linear from 0 to full load. It considers unit number 1, unit number 2, unit number 3, whatever the unit generators I am considering, its input output characteristics are linear is an assumption. Then there is no other restriction. No restriction, machine is available for my requirement from minimum to maximum generation, no other riding factors on that. And startup costs are fixed amount. Now again, startup cost when it comes thermal, when I say, it is again a cooling based startup or a banking based startup kind of thing. Costs are different because we have seen in the earlier discussion. Cooling and banking kind of curve you can see. The cost of startup, if the machine is cooling, blue line, machine was banking, its cost is different. Certain hour and later, one of the method as per your requirement becomes costlier or cheaper, which is known to us. So in that due regard, this statement says startup costs are at a fixed amount. Then it assumes at certain stage, group of units are working with a precise service at time and remaining are off. It means when there were n units for a certain stage, one of the decisions has been taken. Only one unit is functioning, rest all are off. That is the condition. A state consists of group of units with only precise units in service at a time and remaining off. Suppose decision number 2. Precisely decision 1 numbered unit, precision 2 means decision 2 combined with this unit is only 2 units are functioning, rest 2 are off. That's the meaning of it. While the unit is in off state, the startup cost of the unit is independent of the time. Specifically, it remains fixed. This is again to say startup costs are different for machine to machine based on how far or when is that machine was taken out of the commitment in the very last hour, last but 5 hours, 10 hours later or earlier. What is that duration it has been withdrawn from the commitment? How long time has lapsed before I am trying to combine it? That's called as off-state duration is independent. That kind of time is independent. It matters me really because if I say one of the units is taken out, 10 hours later I am trying to use it. For a 10 hours of running, what it was maintained? It was cooled down to room temperature or it was maintained banking. Again restarting it back to online. That is the time required and startup cost required. That kind of independency is assumed. That is not dependent. It is ready to add to me at fixed cost of startup. Then for closing the unit, there will be no cost involved. So really, this is an assumption. Shutdown costs are also important. When the machine is decommitted from the service, so when it is to be cooled down in a series of processes, cooled down to the room temperature or maintained spinning at certain low temperature, there is an investment of fuel, material as well resources. So this cannot be zero, but it is assumed that this kind of calculation for all the generators in the calculation will be considered no cost such. Then it is generally not taken for all the machines. The order of precedence is firm and a small quantity of power must be in operation at each interval. This means this is how the strict priority. So priority number 1. Why you took the decision among the 4 generators? One of the generator you took as your decision. What is that decision you took here? Why you added another generator of your choice? That priority is nothing but strict. You know that adding up of this unit makes me profitable. Adding up of another unit makes me possible. That kind of priority, strict precedence makes the things possible. And also, this calculation assumes that the change in load from unit 1 to unit 2, unit 2 to unit 3 in incremental operational hour is infinitesimally small interval of time is very small. Delta P is small. That incremental change is very small. That is being coped up by the unit like that. So it is very small and assumed. Now, when I say a dynamic programming method in this due regard, let's see how it is mathematically coded. Mathematically, it is coded as, let us say, Fn x. Fn x is cost of production of x megawatt from n number of generating units. This is the derivation like aspect. where X megawatt I want to obtain from N generator. N may be 10 example. So it is divided such that the total X megawatt which I want to obtain, obtained by series of decisions. Take a generator, one of the generator initially, let us obtain certain output from that. If it is not fulfilling your total requirement, again another generator you have to add up, such that first decision what you took, one of the 10 generators, suppose N is 10, cost of production of that I have to calculate. That must be minimum for me, because that my experience says from the N number of generators, which is the priority I should take first, I will fix. It need not be priority. It is the first mere decision. But for being engineering perspective, I must take a decision which is cost effective, even though it is my first decision. It shall not go vague and out of bound. Hence, the first decision what I am going to initiate in this page is, out of the N generator, let us take nth generator only. N may be 10. Let us take, to obtain X megawatt from 10 total generator, cost of minimum generating by N, I divide such that, let us take the 10th generator itself, N equal to 10, which is to obtain Y megawatt, not the X complete megawatt. X may be 100 megawatt demand. What I will do? I will obtain certain Y megawatt, which is say 50 megawatt. 100 is my demand, 50 megawatt I want to obtain from machine number 10, like lowercase f n y. To obtain 50 megawatt from my nth machine, 10th generator, what is the cost of that production? This is my first decision. Suppose I am said to take another one more decision. Take only 2 generators for your schedule. If that is the case, I have left with one more decision. That's all. N is my total decision. Say 10. But I have been given, say, take one more decision to fulfill your requirement. Then how it can be done? Among the remaining N minus 1, 9 generators, I have a target of how much? 100 megawatt is my target. 50 I obtained from last machine, and 100 minus 50. 50 megawatt is the target left on remaining N minus 1 units. Among the N minus 1 units, to obtain 50 megawatt, I have to again search recursively. So 9 machines are remaining. Which of the 9 machines is precisely best for me to obtain 50 megawatt? That is called 100 minus the first decision output. 50 megawatt, 100 minus 50 is 50. 50 megawatt from remaining 9 machines. I have to search. Find out that machine which can do that task, combined with the previous decision, with the 10th machine is 50 megawatt, that will fill my X total. That is being done over here. You can see, let F N minus 1 total X minus Y megawatt is equal to the minimum cost of generation for X minus Y megawatt by remaining N minus 1 unit. It means to say, it states that you have taken one decision and N minus 1 decisions are left for you. Now it is applied this way. The application of dynamic programming method in a recursive relation is total production cost Fn from N generator for a megawatt X is equal to your minimum, should be minimum from a combination of generator. How is that? Inside the flower bracket, the first decision. What was my first decision here? Let us take first decision is my nth machine for a Y megawatt, called Fny. Cost of production for Y megawatt from nth machine, plus this nth machine cannot fulfill your X megawatt because Y is output obtained. So X minus Y is remaining on a remaining machine. That's called again among the N minus 1 machine. Capital F N minus 1. These are the machines remaining to obtain X minus Y megawatt. One among them, I have to pick 2 from them. I have to pick 3 from them. I have to pick as per my criteria. It is written as recursively. Total production cost of X megawatt from N number of generating units in a plant is should be your minimum from the combinational set, like that. cost of production of your first decision for y megawatt plus expected production cost for x minus y megawatt from remaining n minus y machine. So this n minus 1 I have to expand so that this will contain, suppose it is a n capital N equal to 10, then a 10th machine you took as your first choice. You have left with the 9 machines. This bracket, if I expand Fn minus 1, it will have 9 states. 9 states. Among the 9 states, suppose you are supposed to add 1 with previous decision. Among the 9, which is that? First, second, third, sixth, seventh, eighth, ninth. Because 10th is your first choice. So 9 decisions are there. Take the one which is able to cope up with the first decision to meet your requirement. This way, this is expanded and recursively one of them is combined. So using the above recursive relation, we can easily determine the combination of units yielding minimum operating cost for loads ranging in convenient steps from minimum to maximum permissible. This is how the unit commitment mechanism works for your requirement. Then the dynamic programming method, if I say a small example, how an example consider over here, having 4 thermal generating units in a parameter listed in the table. It is required to determine the most economical units to be committed for a load of 9 megawatts. This is to illustrate an example for this kind of relationship. So 9 megawatt is the demand. In steps of 1, 2, 3, in a steps of 1 megawatt, I should solve this using dynamic programming. How is that? You can see. There are units 4. 1, 2, 3, 4 units. Capacity of each unit is minimum of 1 megawatt, maximum of 2. So you can say identical machine. Identical 4 units are there. Then it's the cost function. You know that quadratic form of power fuel cost. F equal to AI plus BI PGI plus CI PGI square, where A, B, C stands as coefficients. Likewise, the fuel cost of unit number 1 is mentioned by coefficients A, B, C and D are not given. So depending upon the type of representation of fuel cost, these coefficients are characterized. A and B are given, C is not given. Then how I can write this? Unit number 1, unit number 2, unit number 3, unit number 4. So how these are used? You can just see this directly. F1 of 9. Just see here. What is this? The equation for fuel cost is half A1 PG1 square plus B1 PG1. It means this stands as fuel cost function. So PG, megawatt obtained from the generator. PG, megawatt obtained from generator. B1, A1 stand here as constants of this machine. So in this case, A1 stand as 0.77. B1 stand as 23.5. Again, A2 for machine 2, 1.66, 26.5. Likewise, A4, B4. Okay. Now, from these machines, you have not been fuel cost, you have been given fuel coefficient. You have to obtain an expression as per the table. So, author has directly created this fuel cost function as half A1 PG1 square plus B1 PG1 as fuel cost format. This is a format. Suppose I have to take a decision from all these 4 generators. Let's say I go back here. My task is to obtain 9 megawatt in steps of 1 megawatt. So what I will do, I will assume from the all these generator 1, 2, 3, 4, total production cost for X megawatt by one of the machine is equal to F1X, means lowercase f1 means to substitute in octane. Production cost from machine number 1, machine number 2, machine number 3, machine number 4, I have to calculate. For that, very simple approach is, let us take my first decision. Machine number 1 is my choice. It becomes capital F1 for 9 megawatt. To obtain whole 9 megawatt from this machine, what is the cost incurred? That is called F1 9. Only one machine dealing 9 megawatt. It is nothing but one machine dealing 9 megawatt equal to F19 from machine number 1, which is equal to half A1 PG1 square plus B1 PG1. A1 B1 I take from this position, which you can see here. This is half, this is nothing but 0.77 divided by 2, which is 0.385. Half into A, 0.385 plus PG1 square, 9 is the megawatt, 9 square, plus B1, 23.5 into PG1. It sums up 242.685 rupees per hour. Suppose if I want to obtain, my decision is machine number 1 for a 9 megawatt. I can calculate machine number 2 for 9 megawatt, machine number 3 for 9 megawatt, machine number 4 for 9 megawatt. When I know what is that machine single, when I take a decision, incur production cost, I can have my rough gauging, or I can simply take whatever the decision I want. Likewise, I can calculate using the fuel cost function, cost of production of 9 megawatt from unit 1, unit 2, unit 3, unit 4. I can calculate using the simple equation like this. Later, let us say, suppose 2 units together, 1 unit together 9 megawatt, this kind of calculation. Suppose I want to obtain 9 megawatt from the machines given to you in 2. 2 of these 4 machines should generate 9 megawatt. That is called obtaining 9 megawatt from 2 machines. That is called F2 with 2, F2 with 9, like that I can do. Let us take obtaining 9 megawatt from single machine stands this way. Same way, obtaining 9 megawatt from 2 units of the 4. How to write it? Like this. F2, 9. Obtaining 9 megawatt from 2 machines in the combination is equal to the combination. 2 decisions you have to take. I can do what I can do. Machine number 2, and I can take as my first choice machine number 2 with a 0 megawatt, machine number 1 with a 9 megawatt. Suppose machine number 1 generates 9 megawatt, machine number 2 not to generate, 9 plus 0. This is the first combination I can do. Because my target is use 2 generator to generate 9 megawatt. In this due regard, my first choice being machine number 1. I know that how much it incur for 9 megawatt. Likewise, I take 9 megawatt from this, 0 megawatt from that. I am combining here 0 megawatt, 9 megawatt. First option. I can do 1 megawatt generation from machine number 2, 8 megawatt from this. You can see F2, 1. Cost of production of 1 megawatt from machine number 2. Total production cost of 8 megawatt from machine number 2. Because machine 1 is your first decision. First decision for 9 megawatt. First decision for 8 megawatt. 7, 6, 5, 4, 3, 2, 1. All you are able to calculate like this. You are ready with that. That is the decision. Because machine 1 is your choice. Machine 1 based calculation for 1, 2, 3, 4, 5, 6, 7, 8, 9 megawatt in steps of 1 megawatt. You are kept ready. Then you combine. Decision is such that I want to work out the schedule by 2 units. Then how I can do? F2 of 9. Working out of 9 megawatt from 2 generators shall be the combination inside a bracket. Second generator being 0 megawatt. First generator being with the 9 megawatt. That is the combination number 1. Square bracket, comma. The another bracket over here. Machine number 2 shall generate 1 megawatt. Machine 1 can generate 8 megawatt. This is the another combination. The other is machine 2 can have a 2, 1 can have a 7. 3 can have a, machine 2 can have a 3, 1 can have a 6. 3, 6, again a 9. Machine 2 can have a 4, 1 by 5. 2 can be 5, 1 is 4. 2 can be 6, 1 is 3. 7, 2, 8, 1, 9, 6. So all the combinations 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 sub-components total inside this flower bracket. Among them, minima of that I have to pick. I have to calculate cost of this parameter, this first option, cost of second option, cost of third, fourth, fifth, and the last one. And if I numerically calculate F20, what is F20? Like this F19, second equation, what is second equation? 1.60, and A2, B2 is 26.5. Like this, A2, B2, PG2, PG2, I have to substitute for 2 megawatt, 3 megawatt, 4 megawatt for a second machine. I have to combine them and put them in the calculation and get one number in terms of cost. Then cost of production of this set possibilities, second, third, and the last possibility. Among the possibilities, compare the least possible combination cost, which is the best for two machines together serving 9 megawatt. It means definitely each machine can do singly, but the option is two should do this task of 9 megawatt. Then what is that sharing among those two? I am trying to work out by dynamic switching over here. Then at the conclusion, I come down from these parameters for a 9 megawatt using two generator. F2 of 9 is best from these calculation as machine 2 can develop 2 megawatt, machine 1 can develop 7 megawatt. Together 7 and 2 lead you 9 megawatt, which is 239.56 rupees per hour. This is the cheapest combination using machine 1, machine 2 for a load of 9 megawatt sharing among them. You may ask me, if I would have used machine 1 only, if I would have used machine 2 only, will it be cheaper or costlier? Yes. The decision is again, if you want to take a decision 1 alone, you would have got comparative cost of machine 1 with machine 2, which is cheaper. That is your best choice. When you are targeted to take 2 decisions, means 2 machines to be used in pair, so that that combination should meet your requirement. You have no option. You must pick the first choice of your own and second choice, which will make the fulfillment of your megawatt with a lower production cost. This is how this set inside the flower bracket, minima outside, minna of these factors I should consider. So similarly, I can do. So for 8 megawatt, this is for 9 megawatt loading. Example is, this is exactly 9 megawatt. So 9 megawatt combination is this. So similarly, I can do 8 megawatt, 7 megawatt, like I can do. So from this recursively, what I get here, so I can get this kind of calculation. Let us take one more simple problem which you will be able to get. Like this table, I have another table. See here. You have been given, determine the most economical units to be committed for a load of 80 megawatt to be supplied by a plant. The load is varied in steps of 10 megawatt. Load is 80 megawatt, steps of 10. The plant has 4 units, 1, 2, 3, 4 like this. Fuel cost functions coefficients are given. Then you have a priority, means you should use first decision as a unit number 1 only for a megawatt, particularly for a load change. Then second priority is combine 2 with 1. The third priority is 3 with 2, 4 with 3. Like this. This is how each unit is having a PG min of 10 megawatt and PG max of 80 megawatt for each. This is a table. This table is having fuel cost coefficient, loading minimum and maximum from generator, and you have load of this much. So how you will address this issue? For this, A, B, like coefficients are given to be put in this cost function. For 1, C1, A1, PG1 square, B1, PG1. Machine 2, C2, A2, B2, like this. I have to put these things. Let's see how it is worked out. For all the steps 0 to 80 megawatt in steps of 10, I have to calculate cost of production of 10 megawatt from machine 1, 20 megawatt, 30 megawatt, 40, 50, 60, 70, 80 from machine 1. Similarly, 10, 20, 30 up to 80, machine 2, machine 3, machine 4. See how it is being done here. You need cost of generation for 10 megawatts from machine 1, cost of production of 20 megawatts from machine 1, 30, 40, 50, 60, 70. This way. Row number 1 refers to different load on plant 1, generator number 1. So it is being shown. You can see from machine 1, 30 megawatt if it is loaded, F1 30. What it is meaning? Machine 1 for a 30 megawatt, what is the incurred production cost? $1065. You can see here. Machine 1, 30 megawatt, 1065. You can see. You substitute and get this. This way, F1 10, this is the 285. F1 20, 640. F1 30, 1065. F1 80. You have to calculate this fuel cost function for different loads 10, 20, 30, 40 up to 80. You will be able to get first row data. Suppose the same thing if I repeat F2, you can see here F2 for 10, F2 for 20, F2 for 80. Second row. This is the second row data. See, you have to initiate a calculation from the fuel cost function of machine number 2 with the 10, 20, 30. Using this calculation, second row is generated. This is a row. Third row for third machine. Fourth row for fourth machine. You have all the fourth row for different load level. Now you are in a decision taking process. How to take a decision? For a certain load of 80 megawatt, what is your combination? First is to calculate for each machine incrementally minimum to maximum in a table of entry. Table of entry. Table of entry. Next step is, this is being done on a fuel cost. Very simple. Fuel cost is given here. This coefficient I fill here is ready. Use that. For small to highest capacity, calculate it. Now take a decision. What is the decision? We first consider unit 1 be on. For first unit only taking care, F1 10, 285, F1 80, 4240. You can see here, 285, 4240. It means, if my decision is first machine be taken for initial application, its production cost change from 10 megawatt to 80 megawatt as rupees 285 per hour to $285 to 4240. Now, we assume that unit 2 is committed. See what is this? F280. I am trying to combine one of the second generator with the first generator decision for what megawatt? 80. Now, it is not the responsibility of the first machine to generate 80. It is the responsibility of the joint machine 1 and machine 2 together 80. This is a joint decision. F2 80, 2 units together 80. Then production cost of producing 80 megawatt with unit 1 and 2. We can meet 80 megawatt with different possibilities. How is that possibility? 0 from unit 2, whole 80 megawatt from unit 1. First option. 10 megawatt from second machine, 70 from machine 1, and so on. You can see, I just go back. When I combine 1 and 2, what are the possibilities? 10 and this is 10 from machine 1, 70 from machine 2, 20 from machine 1, 60 from machine 2, 30 from machine 1, 50 from machine 2, 40 from machine 1, 40 from machine 2, 50 from machine 1, 30 from machine 2, 60 from machine 2, 20 from machine 60 from machine 1, 20 from machine 2, 70 from machine 1, 10 from machine 1, 0 from machine 2, 80 from machine 1. This is how I can combine. This is the combination I am mentioning here. 0 and 80, 10 and 70, so called 80 and 0. So these combinations, if I write in the form of a set, how it look like? Production cost of 80 megawatt from 2 units in the generating station. F2 80, production cost for 80 megawatts from 2 generators is equal to a bracket minimum possible quantity of the combination. What is that first combination? 4240, first possibility. You can check here. 0 plus 4240. What is this? You can just see. 4240 refers to whole 80 megawatts from machine 1. 80 megawatts from machine 1, if I take, it is 4240. Then 0 megawatt from machine number 2. Then 70 megawatt from machine number 1, 10 megawatt from machine number 2. You can see. This is 70, 3465. 70 means it must be 10. This 350 is 10 megawatts from machine number 1. You can see here. You kept ready this one. Then I use it. Then 2730. 2730 refers to 60 from machine 1, then 20 from other side. 60, 20. This is 20 from machine number 2. 860. You can just see. 20 from machine. Very simple. 860. I have added here. Then 2125. What is 2125? 50, 30. This is a 50, 30. This is 40, 60. Again, 30, 50. So you can go on. So all these combinations, when I put together, the last is whole megawatt be from machine 2, nothing from machine 1. 7280 refers to, you can see here. 7280 means entire 80 megawatt is being served by machine 2, 0 megawatt from machine number 1. That is the combination. So you have so many possible states, state 1, 2, 3, 4, 5, and add up and find the minimal cost of this. Minimal cost from this works out 3620. This is the third state. What is the third state? Third state. State number 1, 2, 3. 860, 2760. What is this? 60 from machine number 1, 20 from machine number 2. You can see here. 3620 refers to 60 from machine number 1 and 20 from machine number 2. This together fulfill your 80 megawatt together as a minimal. So therefore, your best unit commitment for 80 megawatt for 2 generators to be taken this care is to work out 60 megawatt from machine number 1, 20 megawatt from machine number 2. This is the first combination I worked out for 80. Now, whenever you are combining 2 machines together in this plant for a 80 megawatt load, this is forever best combination we should remember. So, decision 1 is only one machine. Decision 2 is machine 2 and 1 serving this pattern is the decision 2. If I continue further, what is this? Thus, unit 1 and 2, the best option is to generate 60 megawatt from unit 1, 20 megawatt from unit 2. Suppose load is 70. How to obtain 70 megawatt from 2 generators in this plant? Earlier I had 80 megawatt. Now I have 70 megawatt target. How I can do it? Minimum of second machine 0, first machine 70. Second machine 10 megawatt, first machine 60. Second machine 20, first 50. Are you able to see this? 0, 70, 10, 60, 20, 50, 30, 40, 40, 30, 50, 20, 60, 10, 70, 0. So similarly, I have different sharing combinations from machine 2, machine 1 for a load of 70. Earlier I did a load of 80. If I do a load of 70, similarly I have information for production cost. Production cost I will place here. When I place the production values, I will get the minimum combination of this as 50 megawatt from machine 1, 20 megawatt from machine 2 can fulfill your 70 requirement. This is a recursive process. Why I am going reverse, you may see. 80 is my requirement. What is the next? Minus 70. Next minus 60, 50, 30, like that. Recursively, I will be following 70 megawatt combination by machine 1 and machine 2 can be worked out very effectively by sharing 50 from machine 1, 20 from machine 2. Suppose if I change down 60 to 70 to 60 megawatt. Again, I have a minimum combination of these two machines. Machine 2 0, machine 1 entire 60. Machine 2 10, machine 1 50. Again the same combination 0 and 60, 10 and 50, 20 and 40, 30 and 30, 40 20, 50 10, 60 0. So I am just going from machine 2 being 0, fullest from machine 1, and increasing machine number 1, making the 0 on machine number 1. This way I will have combination set up for a load of 60. Then add these values from the table. This is the table having all this data. 10, 20, 30, machine 1, 2, 3, 4. All these I have here. When I add them in this position, I am sure I will have discrete state values of combination 1, combination 2, 3. There is no doubt these values have been simply taken from the table which is prepared. Once it is observed, the minimum cost of production of 60 megawatt is 2420 by making fixed 20 megawatt from machine 2, 40 megawatt from machine number 1. So this is another option. Then 60 you reverse to 50. When is the 50? 0 and 50, 10 and 40, 20 and 30, 30 and 20, 40, 10, 50, 0. Again you will have different proportional sharing of machine 2, machine 1 for a 50 megawatt. Substitute these values again from the table. This table serves you. Once you prepare this table for a certain expression for machine 1, machine 2, machine 3, you prepare and keep ready.